Hello all, welcome to Ranjana's Academy. Today is the session 4 of Haloalkanes chapter. So I'll be discussing the chemical reactions in this video of all about haloalkanes. So majorly reactions of haloalkanes is divided into three categories: nucleophilic substitution, elimination reactions, and reaction with metals. So in this lecture, I'll be completing the nucleophilic substitution. So in nucleophilic substitution, if you see majorly, you will see the mechanism part in that Sn1 and Sn2 is there. And third category is stereochemical aspects of nucleophilic substitution reaction. First, let us see what is a nucleophilic substitution reaction. You have learned in class 11 that nucleophiles are electron-rich species. So who are nucleophiles? They are electron-rich species. Therefore, they attack at the part of the substrate molecule which is electron deficient. So, if there is a site which is electron deficient, these are rich people, right? They'll go there and they'll act. So, the reaction in which a nucleophile replaces already existing nucleophile in a molecule is called nucleophilic substitution reaction. Haloalkanes are substrate in this reaction. In this type of reaction, a nucleophile reacts with haloalkane having a partial positive charge on the carbon atom bonded to halogen. So what does it have? It has a partial positive charge on the carbon atom bonded to halogen. A substitution reaction takes place and halogen atom called leaving group departs as halide ion. So what happens? The positive charge and negative charge will be identified first in the nucleophile. What happens? They will split into plus and minus charges. So the minus charge, that is the halogen atom, is called as the leaving group. Okay, this will be called as your leaving group. Since the substitution reaction is initiated by a nucleophile, it is called as nucleophilic substitution reaction. How is it called? It is called as nucleophilic substitution reaction. It is one of the most useful classes of organic reactions of alkyl halides in which the halogen is bonded to sp3 hybridized carbon. The products formed by the reaction of haloalkanes with some common nucleophiles are given here. Students, this is the chart which is given in your textbooks where you will be discussing the nucleophilic substitution of alkyl halides. Okay, so you can see a reagent NaOH is given. What is the nucleophile you have to identify? That is OH. Okay, and substitution product will be ROH. That will go off, right? So class of main product is alcohol. What is the product you are getting? Based upon that you have to write. So here it is an alcohol, here it is an ether, here it is an alkyl iodide. You have alkyl group and iodine group, so it's iodide. And primary amine is formed, secondary amine, tertiary amine, then nitrile group. Yes, or a cyanide also you can call it as CN means cyanide. Then RNC, which is isocyanide. Then alkyl nitrite you have to see because an O2 is there. Okay, nitrite. And nitroalkane, you have to understand this is ether and this is ester. Okay, yes. Then you have hydrocarbons, normal one RH. Then R dash is just alkane. Got to know about this? So this is reagent, this is nucleophile, all this you have to understand. Okay, just go through this. Okay, no need to memorize. This is just for understanding the concept better. NCERT has provided this box. Groups like cyanides and nitrites possess two nucleophilic centers. They have what? They have two nucleophilic centers, and these are called as ambient nucleophiles. Actually, cyanide group is a hybrid of two contributing structures and therefore can act as a nucleophile in two different ways. Either like this, either carbon can take the negative charge or the nitrogen can take the negative charge. That is linking through carbon atom resulting in alkyl cyanides and through nitrogen atom leading to isocyanides. Okay, so this will be alkyl cyanides if it links with carbon, and if it links with nitrogen it leads to isocyanides. Similarly, nitrite ion also represents an ambient nucleophile with two different points of linkage. The linkage through oxygen results in alkyl nitrites, while through nitrogen atom it leads to nitroalkane. Very important. Okay, so you have to see what is that. Alkyl cyanides when it reacts with carbon. When it is the nitrogen, It is isocyanides. Likewise, for alkyl nitrites, it is for oxygen, and for nitroalkanes, it is with nitrogen. So you have to understand that. Clear? Okay. Now let us see the mechanism. This reaction has been found to proceed by two different mechanisms which are going to be discussed now. One is Sn2 mechanism and the other one is Sn1 mechanism. So what is Sn2 mechanism? Substitution nucleophilic bimolecular. Bimolecular. What is it? The reaction between CH3Cl and hydroxide ion to yield methanol and chloride ion follows a second order kinetics. What does it follow? It follows a second order kinetics, that is the rate depends upon the concentration of both the reactants. See, here you have OH one reactant and this you have another one reactant. When both of them combine, what happens to the rate of the reaction? It depends upon the concentration of both the reactants. That is what is mentioned here. And what is the product you get as a result? This is your product, right? So the above reaction can be expressed diagrammatically over here. So you can see this is here and this is here. So what happens? They form a bond. That is, your OH and Cl will be at the corners like this and your HH will be attached over here in the center. So what you get here as a result? This is your H, OH, right? And what is this? Your Cl minus gets dissociated, right? Got to know about this? Okay, fine. So the red ball represents the incoming hydroxide ion and green ball represents the outgoing halide ion. Fine. It depicts a bimolecular nucleophilic substitution Sn2 reaction. The incoming nucleophile interacts with alkyl halide causing the carbon halide bond to break and a new bond is formed between the carbon and attacking nucleophile. Here it is CO bond formed between C and OH. These two processes take place simultaneously in a single step and no intermediate is formed. What happens? The two processes take up simultaneously in a single step and no intermediate is formed. As the reaction progresses and the bond between the incoming nucleophile and the carbon atom starts forming, the bond between carbon atom and leaving group weakens. What happens? The bond between the carbon atom and leaving group will weaken. Okay, as this happens, the three carbon hydrogen bonds of the substrate start moving away from the attacking nucleophile. Okay, so in transition state, all three CH bonds are in the same plane and the attacking and leaving nucleophile are partially attached to the carbon. As the attacking nucleophile approaches closer to the carbon, CH bonds still keep on moving in the same direction till the attacking nucleophile attaches to carbon and leaving group leaves the carbon. As a result, configuration is inverted. The configuration of carbon atom under attack inverts in much the way as an umbrella is turned inside out when caught in a strong wind. This process is called inversion of configuration. Fine. Okay. You was reading a big paragraph and I was also listening to it, but I couldn't understand, ma'am. Okay, I'll make it easy for you. Students, it is very simple. So you have a 3 carbon hydrogen bonded, right? The CH bonds are in the same plane. Okay, so they are going to leave the nucleophiles and are partially attached to the carbon. They are partially attached. Okay, now what happens is, as the attacking nucleophile is going to come closer to the carbon, CH bonds still keep on moving in the same direction till the attacking nucleophile attaches to the carbon and leaving group and leaves the carbon. Okay, as a result, what happens to the configuration when the nucleophile comes and attaches? It gets inverted. It gets inverted, students. So it is called the inversion of configuration. So in the transition state, the carbon atom is simultaneously bonded to incoming nucleophile and the outgoing leaving group. Such structures are unstable and cannot be isolated. Okay, what happens? Few structures are unstable and cannot be isolated. Why? Because the nucleophile will be coming, okay, to incoming nucleophile and outgoing leaving group. In the transition state, the carbon atom is simultaneously attached to incoming nucleophile and outgoing leaving group. Such structures are unstable and cannot be isolated. Thus, in the transition state, carbon is simultaneously bonded to 5 atoms. Carbon is simultaneously bonded to how many atoms? 5 atoms, students. Okay, so these are unstable and cannot be isolated, and in transition state they are bonded to 5 atoms. So this is the configuration. Spatial arrangement of functional groups around carbon is called its configuration. Yes, see the structures A and B below, which is given here. So look at the structures here. Can you see? When you keep a mirror, what happens? You can see the inversion. Chlorine comes to this side. It gets toppled up. Okay. From left to right, it gets inverted. Okay. So these are the two structures of the same compound. They differ in spatial arrangement of functional groups attached to carbon. Structure A is mirror image of structure B. We say configuration of carbon in structure A is mirror image of the configuration of the carbon in structure B. Since this reaction requires the approach of the nucleophile to the carbon bearing the leaving group, the presence of bulky substituents on or near the carbon atom have a dramatic inhibiting effect of the simple alkyl halides. Methyl halides react most rapidly in Sn2 reactions because there are only 3 small hydrogen atoms. Tertiary halides are the least reactive because bulky groups hinder the approaching nucleophile. Thus, the order of reactivity followed is primary followed by secondary followed by tertiary. This is exclusively for only what? This is only for your Sn2 reaction, not for any other reaction. Primary halide greater than secondary halide followed by tertiary. This is for your Sn2 reaction. So this is your steric effects in Sn2 reactions is depicted in the diagram. So you can see which has greater one, 1, 0.02 and 0. So 1 has the greater one, that is primary. Okay. Next is Sn1 reaction, students. This is simply unimolecular substitution reaction of nucleophile. Okay. So Sn1 reactions are generally carried out in polar protic solvents. Point to note. They are usually carried out in polar protic solvents like water, alcohol, acetic acid, etc. The reaction between tertiary butyl bromide and hydroxyl ion yields tertiary butyl alcohol and follows the first order kinetics. That is, the rate of reaction depends upon the concentration of only one reactant, which is tertiary butyl bromide. So you can see only depending upon this, the formation of product is carried out. It occurs in 2 steps. In step 1, the polarized CBr bond undergoes slow cleavage. What does it undergo? It undergoes to produce a carbocation and a bromide ion. So what does it produce in the slow cleavage process? It produces a carbocation and a bromide ion. Can you see here? A carbocation and a bromide ion, right? So the carbocation thus formed is then attacked by nucleophile in step 2 to complete the substitution reaction. Now, the step 1 is the slowest and reversible. It involves the CBr bond breaking, for which the energy is obtained through solvation of halide ion with a proton of protic solvent. Since the rate of reaction depends upon the slowest step, the rate of reaction depends only on the concentration of alkyl halides and not on the concentration of hydroxide ions, right? The rate of reaction depends only on the concentration of alkyl halides and not on the concentration of hydroxide ions. Further, greater the stability of carbocation, greater will be the ease of formation from alkyl halide and faster will be the rate of reaction. Important point here. See, greater stability of carbocation, greater will be the ease of formation from alkyl halide and faster will be the rate of reaction. In case of alkyl halides, 3 degree undergoes Sn1 reaction very fast because of high stability of 3 degree. That is, what is 3 degree? Tertiary carbocation. Simple, right? So what do you mean here? What is going to be the reaction? It is going to be the reverse of your Sn2, 3 degree followed by 2 degree followed by 1 degree, right? That is tertiary followed by secondary followed by primary. So we can sum up the order of reactivity of alkyl halides towards Sn1 and Sn2 reactions as follows. This is the order, and this wise if you go till tertiary, it is your Sn1. If you go towards your primary, it is your Sn2. Simple. Okay. For the same reasons, allylic and benzylic halides show high reactivity towards Sn1 reaction. The carbocation thus formed gets stabilized through resonance. So what happens? You got a carbocation which is going to be formed. Yes. Now we are going to see how it gets stabilized through resonance. What happens here? One electron jumps here, okay, to get stability. So this double bond is being formed over here in the next diagram. So what happens? You can see the double bond over here. This has shifted there. Now what happens? This will see, it's like just shifting places. So this will shift to this place because now this place is also vacant. So this place has to be filled so that it will be shifting here. Now what happens to this last one? It will say I will come here. And what happens further? What is the last structure you get which is very stable due to resonances? This is the structure. You get a ring. Here you have a double bond, here you have a double bond, and here also a double bond with CH2. So for given alkyl group, the reactivity of halide Rx follows the same order in both the mechanisms. Yes. See, if you see for halide, it is the same. It is always the same for halide in both the reactions. Only for your base, that is your tertiary or secondary or primary carbon, depending upon that only the reactions or the numbers changes. So here you have some example questions and some in-text questions. Please do give a try. The solutions is already given in the textbooks. In the next section, I'll be discussing about the stereochemical aspects of nucleophilic substitution reaction. If you had understood today's concepts, do give a like and subscribe to this video. Thank you so much for watching.